right, so we're going to start on page 9, and I know we didn't go over 7 and 8 a lot, but we're not worried about 7 and 8 because they're not really important to us. However, everything that we go over for the rest of this set of notes is important. Okay, it is very important. So let's go ahead and get ready and focus today. I'm going to swap it up and use blue today instead of red. I'm tired of red. We've moved past red. Okay, so I'm on page 9.
I feel like blue would be.
So, quantum numbers and atomic orbitals. There are 4 quantum numbers, N, L, M, and S, and we always write them in that order. And I'll go ahead and give you a heads up. I'm going to be skipping around pages, so stay with me. Okay, stay focused today because I'm going to be moving around. I'll try to say page numbers, hopeful, so you don't get lost. So, we've got N, L, M, and S. N gives me the principal energy level, okay? What do I mean by that? The further away we get from the nucleus, we increase in energy levels. So, N also lets me know the distance the electron is from the nucleus. If I'm in energy level N equals 1, then what do I know? I'm in the first energy level, so that means I am what distance from the nucleus? Close, far away? What am I? Close, okay? So N equals 1 lets me know that I'm close to the nucleus. Whereas if I go to N equals 5, I know I'm farther away from the nucleus, okay? What do we know about the energy of an electron when it's close to the nucleus?
It's hard.
It's low. Okay, remember when we talked about the ground state of an electron and how electrons want to be in the lowest energy level possible? That's the closest they can get to the nucleus. Okay, so electrons want to be in the closest they can get to the nucleus. So as I go up in energy levels, the amount of energy the electron has also increases. Okay, so knowing N can also let me know the energy of the electron. Okay. Where do I get N from? It will be really easy. It'll tell you something like it's a 3s electron, so that means N is equal to 3. Or maybe it's a 4d electron, that means N is equal to 4. Okay, so the number always gives me N, so N's always the easiest one to figure out. You with me? You're with me. All right, L is called the angular momentum number, okay? Angular momentum. Now, I like to think of L as more of the shape, okay? L lets me know the shape of the orbital that the electron is in, okay? If L is in the S shape, if it's in an S orbital, that means it is a sphere. Okay, and that also means that L is assigned the number of 0. So that's in your chart right there. If it's an S, then L is equal to 0. Okay. If it's in the P shape, it looks kind of like a dumbbell. Okay. And if it's in the P shape, then we say L is equal to 1.
Do we have any other shades?
Hey, do you get your forms for titles?
No.
There's a little girl on one.
She gave me 1. It's probably on my desk. Check my desk. Is there a form sitting there?
Yes.
There you go.
Alright. Do you need it back?
Yeah, it's cool. All right. So if it's a p orbital, then we say L is equal to 1, right? If it's a d orbital, it looks like we took 2 p orbitals and we put them together. That's d. If it's the d shape, then we say L is equal to 2. And then F I can't draw. I'll show you a picture in just a second. All right, so if it's in F shape, we say that L is equal to 3. F is like a bunch of dumbbells put together. Okay, it's a bunch of them. Can't draw it. You with me? And then, of course, it could keep going on and on and on, G, H, I, J, whatever, but we don't go that far yet. So we can stop at F, right? So it's important you know S, P, D, and F. All right. So L is limited by whatever N is, okay? The maximum that L can be is N minus 1. So what do I mean by that? If I'm in the first energy level, N is equal to what? 1, right? So when N is equal to 1, what are the possible shapes of L that I can have?
B. Wait. That's S.
The only thing I could have is what? S, right? Because what's 1 minus 1? 0. So L would have to be equal to 0. Therefore, the only shape I could have was a S. Do we see that? Okay. What if N was equal to 2? What are my possible values I could have for L? I could have S and P, right? Because I could have L is equal to 1 and I could have L is equal to 0. So that would be the P shape and the S shape. We see how that works? You with me? And then it would keep going from there. Then we move on to M. M is the magnetic number, okay? And I like to think of M as the orientation, okay? M describes the orientation of the orbital in a given space. Here's how you come up with M, okay? You do it kind of like a number line, okay? L is equal to what? 0, okay? So I have one line for S and it is 0. One line for S and it is 0. There's my 1S, there's my 2S. Do we see that? Okay? For P, L is equal to what? 1. So I put my 0 in the middle and I can go from -1 to +1. Do we see that? Okay. So for M, for a P orbital, could be 0, -1, or +1. We see that? Okay. And then if I drew a D orbital, how many blanks do you think I would have to draw?
Do a D.
Mm-hmm.
5 across.
5, right? If I drew a D, it'd have to be 5 because L is equal to 2, so that means I could go anywhere from -2 to +2. 0's in the middle. Do we see that? Everybody with me? Okay. Now, each of these arrows represents a what? Electron. Okay? Each arrow represents an electron. Right? So, if I ask you what is N equal to for this electron that I just circled, what is N? N? 3. 3, right? Somebody said 3. So N is equal to 3. How do I know? Because it's in the what? 3S. Where do we get N from? The number. So that's 3. What shape is this? S, right? So what's L equal to? 0. So I write L. Okay. I get M from these numbers here on the number line. So what's M equal to for this electron? 0. And then the last one we haven't covered is what? N, L, M, S. Okay? S is really easy, and we're going to do this in just a second, but I'm going to write it here so it's all on one page for you. S is equal to the spin of the electron. If it is an up arrow, that means it's a positive 1/2 spin. If it's a down arrow, that means it's a negative 1/2 spin. So for this electron right here that I circled, what would S be? -1. Do you see how we do quantum numbers? Let's talk about this a little bit more. Right, I'm skipping exercise 6 because we already did that and you just didn't realize it when I was doing the notes. All right, so let's look at the shapes again. All right, so we already know S is a what? Sphere. Okay, this is sphere. All right, and so we can see that as the energy level goes up, what happens to my sphere? It gets bigger. Okay, these blank spots in the middle are called nodes, and this is where electrons do not exist, is in the node. Okay, so if you were in the nodes, there would be zero possibility of finding an electron there. Okay, so they don't go in the nodes. All right, and then here we can tell that this is what shape right here? What shape is that? That's a P. And how many different orientations of P can we have? 3. So that's where we got that -1, 0, +1 for M. Do we see that? Okay. M tells me how many different orientations. And then when we look here, we see D. How many different orientations do you see of D? 5. So that's where we got that -2, -1, 0, +1, +2. Do we see that? Does that make sense?
Why is the final one like a circle?
The final one is, D is normally 2 p orbitals put together, but the final one is an S and a p orbital together. That's the difference. And then F, how many different orientations of F do I have?
A lot. There's like 5. No, that's not 5, 7. So.
7. So how many lines? I would have to draw 7 for F. So I have 0, 1, 2, 3, -1, -2, -3. If I was trying to find M. Do we see that? Yes? No? Maybe so? You're with me? All right. So we feel good about this? Yes. All right. So let's go back and look at this for a second. How many orientations of S can I have? 1. How many different ways can I orientate a sphere? Just 1, right? It's just a ball. No matter which way I turn it, it's still the same direction, correct? Because it's a sphere. So in S, I can only have 1 orientation. How many electrons can I fit in an S orbital? 2. So I can only fit 2. 1, 2 is the maximum I can fit in there. Okay. How many orientations of P do I have? 3. 1, 2, 3. So how many electrons can I fit in a p orbital? Maximum. 6, right? 1, 2, 3, 4, 5, 6. Notice when I drew that, what did I do?
You did all up there.
I went all the up arrows first, and then I went back and drew the down arrows. We're going to talk about why in just a second. All right. And then a d orbital, how many different orientations do I have? 5. So how many is the maximum electrons I can fit in there? 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I like where you get the exponents to it.
Yes. Okay. And then of course we just drew out F. How many different orientations of that one? 7. So how many is the maximum number of electrons I could find in F? 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is coming back to us a little bit. A little bit. There should be a little bit. Okay. So this is where we get our what we call our electron configurations. Okay, as we can look in an atom and we can see how many electrons are in it, and we can predict, actually we can write out, okay, exactly which orbitals those electrons would be in and how many would be in each. And we can do that, and we're going to do this today. Okay, all right, so we already talked about electron spin. The electron spin affects the magnetism. Okay. Electron spin affects the magnetism. Remember, we talked about how electrons behave as waves and particles, correct? Yes. And we talked about with electromagnetic radiation that they have an electric field and a magnetic field. So those negative electrons, which we know have an electric field, they're negative, okay, also have a magnetic field. Where does that magnetic field come from? It comes from the unpaired electrons. Okay. So there can be two types of magnetism in a molecule, diamagnetic and paramagnetic. Okay? And a diamagnetic, it's actually, that molecule is no longer magnetic. It's not magnetic. So think of it as diamagnetic, magnetism died. Okay? Why did the magnetism die? Because all of the electrons are paired. Remember we talked about when we draw the up arrow, we say it has a positive 1/2 spin. When we draw the down arrow, we say it has a negative 1/2 spin. So what do those do to each other? They cancel each other out. So it canceled out the magnetism. Okay? Paramagnetic means that there is magnetism, that the electron is attracted to a magnetic field. Why? Because it has one or more unpaired electrons. So let's talk about this down here. Hydrogen is paramagnetic, so that means it does or does not have a magnetic field. Does. And helium is diamagnetic, which means it does not. Why? Well, if we drew the electron configuration for hydrogen, it would look like this. And if I drew it for helium, it would look like this. What do we notice about the hydrogen? You know, it has an unpaired electron, and helium has no unpaired electrons. We see it? We feel okay about it? I feel like I missed. What do you say?
What's
No, I
the
didn't.
ferromagnetic?
Okay, sorry, it got stuck. Now it's not stuck. Alright. So, what about the ferromagnetic? Ferromagnetic just means normally when you introduce something to a magnetic field, it becomes magnetic. Okay? I can make something that's not magnetic by putting it into a magnetic field. What makes something ferromagnetic is when I introduce it, it gets its magnetism even when I remove it. Okay? So even when I remove it, it keeps that magnetic field. And you don't really have to focus on the ferromagnetic, you just need to know the dia and the para. Okay? If you know those two, then you're okay. All right, the Pauli exclusion principle says no two electrons in an atom can have the same set of 4 quantum numbers. Okay? None of them. Even if their N, their L, and their M is the same, what has to be different? S. Okay? Because if I draw one up, if I go to pair it, what do I have to do to it through the other arrow? Draw it down, right? So the S, even if the S is the only thing that's different, the S will always at least be different. So no two electrons in an atom have the same set of 4 quantum numbers. Okay? And then the off-bow principle came along. It's called the off-bow principle, for those of you who just want to know the name of it. All right, and the off-bow principle says that electrons are going to fill in the lower energy levels first, and then they'll increase. Okay, so electrons want to occupy the lowest energy level spot available. That's right here. Each electron wants to occupy the lowest energy space available. So it's going to fill the lower ones, and then it's going to move on to the higher ones. Well, how do I know what's lower and what's higher? The first way I can know is I can do the Christmas tree version. Okay? Y'all remember when we did this last year? We called it a Christmas tree because I think I did it in like red and green ink or something. So let's look at that. I'm going to draw it up here right quick. There we go. Okay, so I start 1s, 2s, 3s, 4s, 5s, 6s, 7s. I draw them all in a line. Okay. Then there's no such thing as 1p, so I start 2p, 3p, 4p, 5p, 6p, 7p. All in a line. You don't have to draw this if you don't want to, because I'm going to show you an easier way. But if you want to draw it in case you want this to be your backup method, if you forget how to use your periodic table method, go ahead. There's no such thing as 2D, so we start 3D, 4D, 5D, 6D. And then there's no such thing as a 4D, as a 3F, so then we go 4F, 5F. Alright, so how do I know what order they're going to fill in? I draw my diagonal lines. Okay. So, 1S fills in first. Then 2S fills in. Then 2P, then 3S. Then 3P, then 4S. Then 3D, then 4P, then 5S. Then 4D, then 5P, then 6S, then 4F, 5D, 6P, 7S, 5F, 6D, 7. Do we see that? And you can just draw it out by putting them all in order. 1 through 7S, then 2 through 7P, then 3 through 6D, then 4F and 5F.
So we won't get like a 6F.
No. This is as far as the current periodic table can go. And they have currently filled in the whole periodic table. So if we discover a new one, then they'll have to add in an 8S here. So then it would go 7P, 8S. 8S comes next. But we haven't discovered anything with 8S yet, so it's not there.
Aren't the using stuff out there just man-made? All the UUs and
Yeah, well, those were actually just fillers, honestly.
we knew something was there, we just didn't know what it was.
Yes, like we knew something was there, we just didn't know what it was, but now it's all filled in, the whole periodic table.
So they're at last level second.
Yeah, they're not real legit. But they are there, and we have made them. So now if anybody else makes one, we're just going to have to make a new row in the periodic table. How cool.
Everything else.
The AP exam is going to have to update their periodic table.
Is the Iron Man one? I can't remember what it's called. Man, element, like the second degree or something.
All right, we good to go? All right.
I'm good for the second.
This is being really slow. Jeez. All right, and then when we are drawing these out, this is the last thing we're going to go over before we start learning how to do this. When we're drawing these out, Hund's rule says the most stable arrangement of electrons is when we have the maximum number of unpaired electrons. So that's why we draw them all going up before we ever come back and add a down arrow. Okay, so that's why, like, if I was drawing out a p orbital, I would draw them going up, up, up before I ever come back and add a down. Okay, because the most stable arrangement is if they're not paired. Why? What is the charge of electrons? Negative. So when I put two of them together, I have two what charges? Two negative charges. What do we know about like charges? They repel. Okay? So why do we not want them to pair up? Because it minimizes the electron-electron repulsions. So the more electrons that we can keep unpaired, the less repulsions we have. Does that make sense? Yes? All right. So, let's do electron configurations. So you can go to the next page. That chart right there makes a whole lot more sense if you know how to do electron configurations. All right, so electron configurations. Electron configurations is when you write it out like this, okay? Orbital notation is when you draw it out like this down here, okay? So electron configuration is when we write it out. Orbital notation is when we draw it out, okay? So let's start with electron configuration first. If you've got your periodic table, and several people in third period had theirs that I gave you last year, so this was already written on it because we did this last year. Okay. All right, so if you've got your periodic table, the best way to do this, okay, is by just using your periodic table. Okay, and I'll show you the simplest way to do it, and it really is simple. Okay, I promise it's simple. Okay, your first two columns on your periodic table are your S columns. Okay, how do I remember that? How many columns are there right here? 2. How many electrons can fit in an S orbital? 2. Okay, now remember, this is helium. Technically, helium could go right there. Okay, so it's still part of the what? S's. Why did we stick it over there on the other side of the periodic table then? Because it's a noble gas and it doesn't react, so it had to be in the noble gas column. Good job, Zach. This column here is your P column. Okay. How can I remember that that's my P column? How many electrons can fit in a P orbital? 6. 1, 2, 3, 4, 5, 6. Oh, this is good. Your transition metals are your D columns. Because how many electrons can fit in a D orbital? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, good stuff. And then those that they pull out at the bottom are your F columns. Because how many can fit in an F orbital? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But F is tricky. Okay? And I don't know why they give you the periodic tables that they do for the AP exam, but that is the one they give you, so therefore that is the one we must use. Okay? If you will notice on your periodic table, they write LA right here. Does everybody see where LA is? And does everybody see where AC is? Okay? LA is lanthanide, and it starts the lanthanide series. So technically, it should be right there. LA. Do we see that right there? Okay. And then AC starts the actinide series, so technically, it should be right there. Okay. So LA would be 4F1, even though it's written up here in this D column. Do we see that? Okay. And then the last two that they write in your F column, this is LU and this is LR. Okay. Technically, these two, let me do this in a different color. These two right here should be right here. Okay. So LU starts my 5D1 and LR starts my 6D1. Okay, so don't let that confuse you. And I'll try to let it not confuse you when we start going over this. All right, we feeling okay? Feeling good? Yeah? All right, we ready to start? Let's start. Now, they already did sulfur for us, but let's go ahead and try sulfur out on our own. So there's sulfur on the periodic table, and it wants the electron configuration. Okay? Sulfur is what number on the periodic table? 16. Okay, it's number 16. So that means sulfur has how many protons? 16 protons. In a normal atom, the number of protons is equal to the what? Number of electrons. So how many electrons does a normal atom of sulfur have? 16. Okay? So if I want to know how many electrons something has, I just go to the periodic table. Okay? And I say, okay, so sulfur has 16 electrons. So then I just go in order to figure it out, and then I can double check myself. So I'm going to write 16 electrons so I can go back and double check myself. Okay? So I start first row. This is 1s what? How many can I fit here? 1, 2. So I start with 1s2. Okay? Then I have to drop down. Next comes 2s2. Okay? Then I go across. What comes next?
3P, so 3P,
What's this?
2P,
2p6. Okay. Then I've got to come back over. What comes next?
3S,
3s2. Then I go across.
3P, 1, 2, 3, 4.
So then I go 3p, 1, 2, 3, 4. Do we see that? So 3p4. So then I can double check myself and add up my exponents. 2 plus 2 is, plus 6 is, plus 2 is,
12,
plus 4 is.
16.
So I know I'm right. Do we see that? That was easy. That's not difficult. We're good. Okay. Now don't forget that we can also do this in noble gas notation. Okay, to make it a little bit easier. Now in noble gas notation, remember you pick the noble gas that occurs before the element you're looking at. So I was looking for sulfur. What's the noble gas that occurs before sulfur? Neon, right? Right here? Neon? Okay. Now it can't be argon because argon happens what? After. So it's got to be neon. So we would put neon in brackets, and then we would just do the configuration for everything after neon. So after neon comes 3s2, and then comes 3p4. Do you remember that? Okay. And most of the time on the AP exam, they're not going to specify which one they want. They'll let you do whichever one you want. So you can choose and say I'm good with either or. All right. If they are specifying, they'll tell you to write out the complete electron configuration, which means they're telling you I want it completely, no noble gas. Or they'll tell you, normally they will never say you have to use the noble gas one. Okay. But most of the time they don't care. They're okay with either one that you do. Do we understand both? Sometimes it's just easier to do the noble gas, especially when it gets really long. And you'll see that, because after cadmium, I'm just going to use the noble gas. But we're going to do cadmium together, and then we'll see how it looks like. So the next one we're going to do is cadmium. Okay? So cadmium is number 48 on your periodic table. All right. So let's start it. What am I going to start with? 1s2. What comes next? 2s2. What comes next?
2P6,
2p6. What comes next?
3S2,
3s2. What comes next? 3p6. What comes next?
4S2,
4s2. What comes next?
3D,
3d.
3D, 10.
10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What comes next? 4p6. What comes next?
5S2,
5s2. What comes next?
49. Yeah, 49. No, 10. It's 10.
We want to count that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
It's 10.
We see that? And do you see how long it gets? Okay, so imagine when you start picking up the ones down here in the F columns, okay, and the 5Ds and the 6Ds. It gets really, 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 really long. So does everybody have this? Because I'm about to erase it. You got this? All right, so let's say we were going to do this with the noble gas configuration. Okay, We look at cadmium and we say, okay, what's the noble gas that happens before cadmium?
Like say one time? Say that question?
Krypton, right? AR? What's the noble gas that happens before cadmium?
Okay, now.
So the krypton, right? So I would just put krypton in brackets, okay? And I would say what comes after krypton? 5s2, and then 4d10. We see how that shortens it a lot, okay? And it's a lot less that you have to write.
Will they will majority of the time on the AP exam, will it be noble gas notation? Or will they say, you need to write the whole thing out?
They'll normally not specify and let you do whichever one you want to.
Also, we just do the last two that come before it?
You just do whatever comes after the noble gas until you get to the element that you're doing the configuration for.
Oh, okay.
That's easy.
Okay. All right, I've written all over my periodic table. All right, so the next one we're going to do is LA. Okay, let's be careful and let's not let LA trick me, because even though they have LA right here, where do I know it really should be?
It should be up there right next to it.
The very beginning of my F. Okay, so let's do this. What's the noble gas that occurs before LA?
Next. Yeah.
There you go, Xe, xenon, right?
Xenon, yeah.
Sure, I'm doing it.
It's right there.
So I'm going to put xenon in brackets. What comes after that?
6s2.
6s2, and then be careful what comes next.
4f.
4f1. Do you see how we have to, after 6s, we've got to jump down to the f's before we can ever come back to 5d. Do you see that? So this would be 6s2, 4f1. Yes, Ty?
Oh, I see how that part goes.
Yes. This part essentially goes right here on the periodic table after 6s.
Do we have to write like the 4F1 or can we just write 4F?
You have to write 4f1. You have to write the 1. Alright. We good? We see that? So let's try HF. Alright. So which noble gas occurs before HF? Xe. What happens after Xe?
6s2.
6s2. What happens after 6s2?
4f14.
4f14. Excellent. Don't forget, after 6s, I've got to jump down here, and then be careful. What's my HF going to be?
2.
5d2. It's going to be 5d2. Remember, this last one down here starts my 5d1, and so HF would pick up at 5d2.
Oh, okay.
Okay? All right. I feel like we're getting good at this. So let's do RA. Where's RA at? Here it is, right here. RA. So what's the noble gas that occurs before RA?
RN.
RN or
RN. So I'm going to put RN in brackets. And what happens after RN?
7s2.
7s2. RN. Radon. And then the last one we're going to do is AC. And we're going to be really careful there because we know AC really starts the what?
no 5.
The 5F. Okay? So I'm going to put my RN. That's my noble gas that occurs before it. And then I'm going to go, what?
Gonna go
Seven.
It's 6.
7s2.
Oh my.
And then 5. No.
5D. No.
5.
5L1.
5F1. There you go. We're feeling good about this, right?
Yeah.
Yes? We're feeling great?
You're so nervous.
I like it.
You're so nervous. Like, You're
Me?
nervous that we're not gonna get it.
I am. I want you to get it because it's simple and it just.
This is
If
all
you
we
get this, then you can get the rest of this unit a lot better.
got?
So, and if you understand this and you understand bonding, this is important for us to get. Okay, it's really important.
Bonding.
All right, so now let's talk about orbital notation and how we draw them. Okay, so all we did was take our notation. So up here, my sulfur, my 1s2, 2s2, 2p6, 3s2, 3p4, and I drew them out. How many orientations can there be of an s orbital? Just one, right? So I just draw one line. Okay, so there's my 1s. How many electrons were in it?
Two. That's
Two.
what I-
So I did an up arrow, down arrow. Okay. Then comes 2s. How many electrons can go in it?
2.
2. Up arrow, down arrow. Then comes 2p. How many orientations can I have in a p orbital? 3. So we draw 1, 2, 3.
You got me messed up now.
Okay. And then we would go up, up, up before we ever come back
Down.
and do down, down, down.
You gotta know that.
Then we've got 3s. We go up, down. And then be careful, we've got 3p. So we go, there's only 4 of them, remember? For sulfur, it was 3p4. So we said 1, 2, 3, 4. So we drew the last arrow down.
Oh,
And don't you have to circle? Like you have to circle.
Huh?
In that thing that you have to circle.
You don't have to. Here's what they do a lot of times on the AP exam is they will say, write the set of quantum numbers for the last electron drawn. Okay, so that's why normally I'll circle the last one, just in case that's what they ask me.
Wait,
You don't have to circle it.
so they ask that when you write 3p.
So if they ask me that, okay, what's in for this electron that I just circled? Let me do it in a different color. Okay, this electron, what's in for that? 3.
3.
Right? How do I know it's 3?
It's
It's 3p. Okay. What's L?
If it's 3.
1.
1. Okay? Because it's a P shape. What do we assign L if it's P? 1. Okay? Right? What's the M? -1. Remember, we get M from the number line that we draw at the bottom. And what is S? -1/2 because it is a down arrow. You got that? All right. Let's draw cadmium. Okay. Now, when we did cadmium, we did krypton, Kr. Then what came after that?
5s2 and 42.
So 5s. And did we fill that up? Yes. So we go up, down, and then came what?
40.
4D. So how many do I need to draw for D? 5. And how many did I put in there? 10. So I'm going to go up, 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 down, 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 down. Now, let's pretend it asked me for the quantum numbers for the last electron that I drew. So I like to go ahead and circle that electron so I don't get confused about which one I'm working with. What is N for this? 4, right? It's 4D. What's L? Huh? 2. Okay, because it is a D shape, and what do we give L when it's a D shape? 2. Okay. What is my M for this? +2, right? I put the 0, -1, -2, +1, +2, so it's a 2. And what is my S? -1. We okay? So let's do LA. All right, so LA, the noble gas that occurred before it was xenon. And then came what?
6s2 and 4.
6S2, and then 4F1. So we've got to draw how many lines for the F? 7. Did we fill up 6S?
Yeah.
Yes. So we go arrow up, arrow down. And then what am I going to do for F?
Just one.
1 arrow up. So let's pretend it asked me for the quantum numbers for that one. So I'm going to find the last one I drew and I'm going to circle it. Okay? Now don't circle it unless they ask you for it. Okay? Then you circle it. So what's N going to be for this one?
6. Oh, wait, 4. My bad.
4.
Yes. Oops.
Okay. What's my L going to be?
3.
3, because why?
Because it's an F.
Because it's an F, and L is equal to 3 for F. What's my M going to be? Negative 3. I can draw my number line. And what's my S going to be?
Positive 1.
Positive 1/2, since it's an up
I
arrow.
think that I know like to do like the N one is more like
How do I get the L?
the N, like the 4.
The 4? Because it's a 4F, so I get the
So
4 from right there. Alright, let's do HF. For HF, we had xenon that occurred before. Then we went. What happened after xenon?
6S.
Was it 6S?
Yes, ma'am.
Then what happened?
4F.
4F what?
14.
14. So 1, 2, 3, 4, 5, 6, 7. There's 4F. And then what happens after that?
A lot of it.
What came after 4F?
5D.
So 1, 2, 3, 4, 5. I'm almost really dry. Alright, so did we fill up 6S?
Yes.
Yes. Then we filled up 14. Up, 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 up,
Down.
down, 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 down. Okay. And then it was 5D what?
2. What, what?
2.
Yeah,
Yeah,
2.
there's 2.
So I'm gonna go up
Up.
and up.
That's it.
And you know what we're gonna do next?
Do the circle up down
We're gonna
here.
do the quantum number, so I'm gonna go ahead and circle it. What's N equal to here?
5.
5, right there. What's L equal to?
2.
2, because it's D. What's M equal to?
-1.
-1.
Just kidding.
You don't.
And what is S equal to?
I got that.
I'm hoping we're feeling good about this.
Yeah. 15.
I think we should do a test solely on just
No.
A test solely on just
Yeah.
this.
Oh.
just arrows and letters.
I thought he was talking about
Just arrows and
this.
All right.
We were all-
Yeah, just give
So
us.
I think you are good enough that you can do RA and AC on your own. I'm feeling good about it. So you work on RA and AC because you got about 2 minutes till the bell rings. So try it on your own, and if you need me to check it, if you're not comfortable, I will be happy to go do that. Okay? Hopefully you can send me a picture and ask me if you're correct if you want me to check it. All right.